The concept of the fourth spatial dimension has long been a source of fascination, confusion, and endless diagrams of tesseracts. For over a century, the standard explanation has been that it is a direction at right angles to length, width, and height, a new axis that we, trapped in our three-dimensional bodies, cannot point to or visualize. While mathematically sound, this explanation has left generations of students and curious minds with a sense of permanent puzzlement, and for good reason. It describes something genuinely unvisualizable and physically unreachable. However, a significant reevaluation is emerging from the philosophy of science, arguing that the fourth spatial dimension can be reinterpreted not as an abstract orthogonal axis, but as the geometric trace of motion itself. This shift moves away from teaching an unreachable direction and instead grounds the concept in the visible, dynamic world we already inhabit, bridging geometry, physics, and perception in a way that is immediately visual and physically tangible. The traditional model of dimensions, which dates back to the work of Bernhard Riemann, who delivered his groundbreaking lecture in 1854, described dimensions as multiply extended magnitudes that could be extended once, twice, threefold, and, by natural continuation, for times or more. Each new extension conferred a new capacity of being, not necessarily another right-angled direction, but a new, measurable way for existence to unfold. This framework was later adapted by Charles Howard Hinton, the mathematician who coined the term tesseract in 1888 and developed elaborate methods to help people visualize a fourth spatial dimension through color-coded cubes and mental training exercises. Hinton's work was profoundly influential, but it was also deeply rooted in a purely geometric, static conception of the fourth dimension. The orthodox view of the fourth dimension was perhaps most famously popularized by Carl Sagan in his landmark documentary series Cosmos. In a memorable segment, Sagan used the analogy of a two-dimensional flatlander struggling to comprehend a three-dimensional sphere, and then explained that a three-dimensional cube could be projected through a fourth physical dimension at right angles to the three known directions. He admitted that he could not show the audience what direction that was, but he could show them the three-dimensional shadow of a four-dimensional hypercube, or tesseract. This shadow, which appears as two nested cubes with all vertices connected by lines, has become the iconic representation of a tesseract in popular culture. As Sagan explained, the real tesseract in four dimensions would have all lines of equal length and all angles at right angles, but our three-dimensional projection necessarily distorts this reality. This explanation, while elegant and powerful in its own right, has also left many feeling that the fourth dimension is fundamentally inaccessible, something we can only glimpse through mathematical shadows and projections. This is precisely the conceptual gap that the motion-based framework seeks to close. Rather than positing an abstract and unreachable fourth direction, it proposes that the fourth spatial dimension is the capacity for motion itself. Drawing on historical sources from D'Alembert, Lagrange, Riemann, Hinton, and Minkowski, as well as modern applications in animation, physics engines, and space-time constraints, this new framework argues that our pedagogical and conceptual story about dimensionality has lagged behind the mathematics we already use. We already treat the motion of 3D objects as a four-dimensional geometric process in fields like computer animation, robotics, and physics engines. The formal tools are in place. What has lagged behind is the story we tell about them. To understand this shift, it is helpful to revisit the relationship between space, time, and motion. In his theory of special relativity, Albert Einstein unified space and time into a single four-dimensional continuum known as spacetime, where time is treated as a fourth dimension. This was a profound revolution in physics, but it also created a certain amount of confusion. In the spacetime model, time is a non-spatial capacity for duration that, together with the existential capacity for space, enables a new spatial capacity, motion. When a three-dimensional object exists within spacetime, it gains the capacity to move. The motion-based framework proposes that this capacity for motion, enabled by spacetime, is the true fourth spatial dimension. It is not that motion is a separate or abstract dimension, but rather that the geometric traces of a moving object through spacetime effectively constitute a four-dimensional structure. This can be visualized by returning to the analogy of the tesseract. In the traditional view, the tesseract is formed by taking a cube and moving it through a fourth direction at right angles to its three dimensions. In the motion-based view, the tesseract is formed by taking a cube and moving it through space and time. The 4D edges of the tesseract are not extensions into an unreachable direction. They are the paths of motion between an initial state at one point in time and an end state at another point in time. Each vertex of the tesseract traces a world line through spacetime. If the cube remains stationary, the world lines are purely temporal, simply indicating the passage of time. But if the cube moves through space, the world lines become displacement vectors, indicating both direction and distance. The resulting four-dimensional structure is a perfect record of the cube's motion history, a geometric representation of its transformation through space and time. This interpretation has profound implications for how we understand higher-dimensional geometry. Instead of treating the tesseract as a static, unreachable shape, we can treat it as the representation of a three-dimensional form in motion. This is, in fact, the geometry of animation. Every animated sequence is a four-dimensional object, a series of three-dimensional forms changing over time. A moving cube, a rotating sphere, a dancing figure. All of these are four-dimensional objects in the motion-based framework. This makes the fourth dimension not only visualizable, but immediately accessible, present in every moving object we observe. The framework treats time as a metric rather than a separate dimension. The coordinate system becomes x, y, z, t, where the fourth axis encodes motion vectors. Time is how we measure motion, and motion is how we measure time. So in a sense, we are using motions to measure other motions, and we call the observation of it time. As long as things move, time will remain part of our method for describing spatial change. The philosophical lineage of this idea can be traced back to ancient thinkers who recognized the intrinsic link between motion and the passage of time. Aristotle, writing in the 4th century BCE, defined time as the number of motion in respect of before and after, grounding it firmly in change. If nothing moved, he reasoned, time would not pass. He also classified motion into 5 types: upward, downward, contraction, expansion, and locomotion. This inclusion of contraction and expansion, forms of internal transformation rather than mere external displacement, anticipates a self-relative view of motion that modern kinematics has often overlooked. Later thinkers like Nicole Oersma in the 14th century sought to describe motion as a geometric phenomenon in its own right through graphical methods, and Galileo's experiments with falling bodies and Newton's formalization of the force-motion relationship built on this foundation. André-Marie Ampère named the field of kinematics in the 19th century, and engineers like Franz Rielos and Ludwig Burmester further advanced the field by treating motion as systematic transformations in space. The motion-based framework also offers a bridge to exploring even higher existential capacities. Just as motion is proposed as the 4th spatial dimension, force can be understood as a 5th existential capacity, possibility as a 6th, and intelligence as a 7th. Force is what initiates, stops, or alters motion, and in a 4-dimensional world where motion is the fundamental spatial capacity, force becomes the next logical extension. It is the capacity to change the motion of an object, to redirect its path through spacetime. Possibility, in turn, is the capacity for forces to act in various ways, representing the potential for different paths and outcomes. And intelligence is the capacity to perceive, anticipate, and manipulate these possibilities, navigating the complex space of potential motions and forces. This progression from physical reality into the realm of mind and meaning represents a coherent dimensional framework that extends from the geometry of motion to the cognitive capacities of intelligent beings. The practical applications of this framework are already evident in fields like computer animation and robotics. In animation, the motion of objects is represented as a 4-dimensional process, with keyframes marking positions in space at specific points in time, and interpolation algorithms generating the smooth motion between them. The resulting animation is a 4-dimensional object, a series of 3-dimensional forms changing over time. In robotics, The planning of paths for a robot arm involves considering the arm's position in space at each moment in time, effectively navigating a four-dimensional configuration space. Physics engines simulate the motion of objects through space-time, calculating trajectories, collisions, and responses to forces. These are all examples of treating motion as a four-dimensional spatial capacity, even if we do not always articulate it as such. Despite its elegance, the motion-based framework does have limitations and challenges. One of the key objections to the traditional orthogonal axis model is that it describes a direction we cannot visualize or point to. The motion-based model addresses this by grounding the fourth dimension in something we experience constantly, but it still requires a shift in how we think about geometry. A moving object is not just a three-dimensional object that happens to be in different positions. It is a four-dimensional object whose form is extended through time. This requires a more dynamic and fluid conception of form than we are accustomed to. Furthermore, the relationship between time and motion is deeply complex. Time is how we measure motion, yet motion is also how we measure time. This circularity is not a flaw but a fundamental feature of the physical universe, and it requires careful handling to avoid paradoxes. Additionally, some may argue that this framework, while pedagogically useful, is not a true description of the fourth spatial dimension as it is understood in mathematics and physics. In mathematics, the fourth dimension is an abstract space with four orthogonal axes, and a tesseract is a four-dimensional polytope with a specific geometric structure. In physics, the fourth dimension in general relativity is time, but it is a non-spatial dimension, treated differently from the three spatial dimensions. The motion-based framework is thus a reinterpretation of the fourth dimension as an emergent property of objects moving through space-time, rather than a fundamental property of space itself. The motion-based interpretation of the fourth spatial dimension is a powerful and transformative idea. It invites us to see the fourth dimension not as something we must discover, but as the ever-moving world we already inhabit. It unites the mathematical formalism of the tesseract with the physical reality of space-time, treating the 4D edges as displacement vectors tracing paths of change. It moves away from the abstract and unreachable and towards the concrete and visible, closing the gap between the geometry we already use and the reality we already live in. It bridges geometry, physics, and perception, arguing that the fourth dimension is not inaccessible but visible in the dynamic world around us. This shift in perspective has profound implications for how we teach, visualize, and conceptualize higher-dimensional geometry. It suggests that the greatest barrier to understanding the fourth dimension has not been the limitations of our spatial intuition, but the limitations of the story we tell ourselves about it. By telling a new story, one grounded in the motion and change that define our everyday experience, we can make the fourth dimension not only comprehensible but tangible.